same internal grant that we obtained for educational purpose on our ME Lab 2. Team number 2, you guys ready?
Right there.
Right, you guys have 15 minutes to tell us what you guys did on the last 2 semesters. Go, thank you.
Good morning, everyone. Thank you for being here with the Kululu from the TLA project. My name is Stephanie.
My name is Rachel.
Daniel.
Hassan, and Brandon.
In this presentation, we're going to go over motivation, objective, design, simulation, testing, controls, data, economics, and conclusion. Our goal was to create a cooling system that will have controls for flow, temperature, full automation, and data collection. It was also designed to be integrated into a multi-system water heat exchanger for laboratory use. Previous students like us were using the RMFL DLMX learning system, and to get cold water, we'll rely on the water faucet temperature or in actual increased temperature, which is not easily controllable or accurate. Reason why we wanted to replace this system with our system to provide the user with full controls for flow and temperature via user-defined control parameters. Our system objectives are a flow range from 1 to 15 liters per minute, a temperature range from 5 to 20 degrees Celsius, and a maximum pressure of 60 psi.
We started out our preliminary design with the KISS method. We wanted to keep it as simple as possible, so this was our first iteration. We selected our basic components such as a chiller, tank, and pump for their flow range and for their feasibility with economics. We went through several iteration processes, adding components as we went to make our system match what we wanted to achieve. This is our final prototype. We added an air bleeder vent. We added a pressure reducing valve for safety. We also changed the tank that we used, added sensors, and added different valves to connect with the heat exchanger screw. This is what our prototype looks like. While it was functional, it wasn't compact and it wasn't mobile.
After our functional prototype, we started collecting some theoretical data. We did that on our prototype. We ended up calculating a head loss of 1.62 foot, and on our final iteration, we calculated out to be 2.64 foot of head loss, and that was calculated at 15 liters per minute. We wanted to get that at our maximum flow rate. We also calculated it out for the system to go from an ambient temperature to its operational temperature of 5 degrees Celsius, calculated out to take approximately 43 and a half minutes. On our CFD simulation, we ran it several times between 1 and 15 liters per minute. We saw again a head loss of 0.017 foot and a maximum of a little over 2.6 foot of head loss. On the thermal side, we ran it at 10 liters a minute, and we saw that the system actually ran stable at a 10 degrees Celsius difference between the inlet and outlet on our system. For our FEA analysis, we did analysis on the PVC at 60 psi just to see what it would do under its maximum pressure. We saw a maximum hoop stress, a minimum of 90.6 psi and a maximum of 367, which gave us a safety factor of 15. For the long stress, we saw a minimum stress of 10.7, a maximum of 93.7. Again, we saw a safety factor of 15. That led us to take what our functional prototype was to this assembly drawing that you can see here, and then our final design that you can see there, as well as here in front of you.
Okay, for our final design, this is the final prototype from the top view. On the left-hand side, we have the electric panel, and on the right-hand side, we have the piping system. For the piping system, the system is being provided by a pump, which controls a steady pressure, and we also got a pressure reducer, and we also have a 3-way valves to control the flow. We also have an air bleeder for safety purposes, and the system is being provided by a temperature sensor and a pressure sensors throughout the system. For the electric panel, the whole system is being controlled by a data acquisition controller, and also we have a 3-pole contactor, and also the contactor is being controlled by a 5-volt relays for safety purposes. And we also have a transformer to kick off the controllers, which controls the chiller, the heater, and the pump. And we also have a 24 AC to DC converter, which supply power to the pressure sensors and the piping system. We also have complex specification components such as the chiller, We also have simpler ones such as the pump, and we also have electric components such as the contactors. For more details, you can refer to the part manuals.
And to make sure that our system work at the spec, we run some tests over it. And this one is a cooling test that we had done. And it took about 72 minutes for us to cool down like 10 gallons of water from 20 degrees Celsius down to 5 degrees Celsius. And also during that time, the pressure dropped from 7 psi to 5 psi. And we also do the heating test. The temperature raised from 12 degrees to 19 degrees, and the pressure also raised up from 5.3 to 6.6 psi. And this process takes about 26 minutes. So to have the automatic control on the system, we build a lab view program that you on the logic block on the left side, and then on the right side where we collect all the data and calculate it into the value what we want to have. And the value we can change it or adjustable by the user interface of the lab view. On the first line you see a user can disable or enable the system, and then they can set or change the set temperature and also the flow rate. On the bottom left, people can see what running or not, and on the central we see the temperature, current temperature, flow rate, and pressure.
We have two manuals. We have the operations manual, in which you can learn how to safely operate our system and understand what's going on within it. And we also have the parts manual. In case something happens to our system, you can always have access to a specification and information on our components. And if you need to replace any components, and the back of the parts manual does a replacement plan. The system specifications are an electrical rating from 110 to 120 volts, a maximum power of 1,520 watts, an operating temperature of 5 to 25 degrees Celsius, a rate of flow from 1 to 8 liters per minute, and we were using the LabVIEW software. And the weight for our system without water is 130 pounds, and with water is 205. Okay. The economic feasibility that we analyzed for our system from prototype to final design is $26,349, and if we were able to mass produce it will go down to $3,666.
To finalize, we were able to successfully design, fabricate, and test our system not once but twice. And we were able to meet or exceed almost all of our system objectives, and now our system is ready for integration, and we have tested it with the shell and tube heat exchanger system, and it's able to be fully integrated for laboratory use.
This group was flying. Any questions?
Yes, sir.
Okay. Just a simple question. Is there anything in the market, and how does your system compare to it?
On the market itself right now for an educational system, as far as we know, it's just the DLMX. It is what the school uses right now, which doesn't really offer any automation or data acquisition or anything like that. That was the entire purpose of this, just so we could supply higher flow rates, actually monitor pressure, monitor temperature, and collect that data.
One item that I want to hit is the cost. I didn't see much on this. I missed it. Between a system that you purchased and the one you just built, is there a difference? Have you made any savings? Cost, money, dollar?
Yes, between,
The DLMX system and ours.
I am on the DLMX, I believe one unit is what, $2,000, and then one actual cartridge is another $2,000. So you have 6 cartridges. That's $12,000, just right there. Future advancement would be to make this actually capable of integrating into multiple heat exchangers at the same time.
Do you have a cost now? How much this cost?
$3,000. $3,666. For mass production, for our time and labor was $26,000.
That's what I was looking for. Yeah.
So you mentioned that you're using a 5-volt relay for protection. Why did you make that choice?
Because
Because the DAC system, they are not output enough current to kick the contactor, so we use either the amplifier to amplify the current, or we use the 5 volt to kick off the contactor.
the contactor would turn on, turn off. Like it's gonna keep going for safety purposes. Like it turns off until we meet a certain amps.
So if it's safety, does it prevent an arc or something like that?
No.
I mean, then what's unsafe about it?
For the contactor don't burn out.
Okay.
So like the contactor, like
So it's the same
we
thing.
tested it out before the 5 volts. It will keep turn on, turn off.
We're using it as a pilot relay. That way we don't pull as much current through the DAC.
Okay. So there's no danger to the user?
No.
No.
It's to the system.
It's for the system.
safety for the
It's
system.
for the system.
Can you go to 25, please? Yeah, I was looking at this and wanted to ask a question on it. For instance, under current temperature, you have in the middle 2 heat exchanger, and then to the right, from heat exchanger. The from heat exchanger, that's just informational, correct? That's just something you do for the user to see.
Yes.
You can't obviously control that. What you're controlling is to the heat exchanger.
What we're controlling is the tank into the heat exchanger. The from heat exchanger is for informational purposes, for the laboratory settings.
Where are you picking up that temperature to heat exchanger?
So within our piping,
Can you go to the piping diagram? Because I'm tall. Pressure sensor, temperature sensor, pressure sensor, temperature sensor.
So, okay, head back to 25. Can you explain to me when or why the tank temperature would differ from the 2 heat exchanger temperature?
Difference in thermocouple, just a variance.
Because right now we not run to the supply, so
Okay, a bypass?
yeah, not bypass
That
right now. So
Three-way valve is in there. Basically, we're adjusting flow out to the heat exchanger through mass flow. So that three-way valve either delivers to a heat exchanger or back into our system and just circulates within our system itself.
Okay. Okay. I'll talk to you more about it. No, looks good, thank you.
Any other questions?
Yes, sir.
I'll ask the same question that the first team had. What was your statement of purpose? What was the problem you're trying to solve? Scope. One statement.
We were trying to control flow and temperature since in the previous learning system we were not able to we had to go and open the water faucet or put ice in the water to cool the water. Instead we created this system so we can control flow temperature and then we can automatize it and collect that. And of course this goes along with all the other TLA projects such as the heating team, the heat exchangers, cooling tower.
So if I want to restate what you just said in a different time, let's say, the objective of this system was, or the goal, to allow more data collection.
It was to replace the old system with our system.
The,
So that
the,
we-
the purpose of the project in a 1-sentence statement would be to have an entire system that has full automation and data acquisition capabilities for a heat exchanger laboratory system.
So when you say full automation, you actually can drive the system and get the data and do a feedback through your computer or the system sitting there.
You input your temperature and flow that you desire, you turn on the system, and it handles the rest.
Very good. So now I follow that question, but you don't have to answer. Can I do this while I'm sitting in Tyler and this is sitting in Houston?
That is our ultimate goal. That is why we implemented it within LabVIEW. It's will eventually in the future move to a virtual desktop.
Excellent. Thank you.
You're tired of driving, huh?
All right.
Ready?